Exponential growth and decay functions. Here are your state standards. To be successful today, you need to be able to identify and graph exponential growth and decay functions. You need to be able to write exponential growth and decay functions, and you need to be able to solve real-life problems using exponential growth and decay functions. Here's the vocabulary that you need to be familiar with. Make sure you get these in your notes. Exponential function has the form y equals ab to the x power, where a is not 0 and the base b is a positive real number other than 1. Exponential growth function, if a is greater than 0 and b is greater than 1, then y equals ab to the x is an exponential growth function, and b is called the growth factor. So again, if you have this form, your x is your variable. If you have two numbers, a cannot be 0, but if it's greater than 0, that means it's positive, and b is greater than 1, that's your growth factor. That means you have exponential growth. You have an asymptote as a line that as a graph approaches more and more closely. As x approaches negative infinity, f of x approaches 0. And you can see right here, exponential decay, it's approaching 0. And you can see here, it's also approaching 0 there. Exponential decay function, very similar, just going to be going down instead of up. If a is greater than 0 and b is between 0 and 1, then y equals ab to the x power is an exponential decay function. And b is called the decay factor. So remember, b cannot be negative. It has to be a positive real number. But if it's a fraction, if it's between 0 and 1, it's a decay. And if it's greater than 1, it's growth. It can't be 1 because 1 to any power is just 1. It wouldn't be exponential growth or decay. So it can't be 1, but it can be between 0 and 1 to be decay, greater than 1 to be growth. Example 1, graphing exponential growth and decay functions. Determine whether each function represents exponential growth or exponential decay. Then graph the function. All right, so we can see here that the base is 2. That's greater than 1. So this is going to be an exponential growth function. B part, 1/2 is between 0 and 1. So this one would be an exponential decay function. All right, as always, you can make a table of values and you can graph the function using a table of values. To save a little time, I'm going to use my calculator here just to graph this. And then, as always, you can look at the table of values if you want to get some points to sketch a graph on your own. But we're going to do 2 raised to the x power. And going to hit graph. You can see how this grows exponentially after it goes through the y-intercept. Let's go ahead and graph b as well. So we're going to graph 1/2 raised to the x power. This one's going to be the line in red. You're going to see how this one is a decay function because it comes down and approaches the x-axis, where the other one was a growth function. This one is a decay function. And again, if you wanted to see your table of values, now we have 2 graphs in here. You can see the blue and the red. The exponential growth is in blue. Exponential decay is in red. You can see how the numbers in blue, the y values are getting larger exponentially. And you can see how these numbers are getting smaller and smaller and smaller. As they're approaching 0, they will never get to 0, but they are approaching 0. So you see it gets closer and closer to 0. This is in scientific notation here. Example 2, modeling real life. The value of a car, y, in thousands of dollars can be approximated by the model y equals 25 times 0.85 to the t power, where t is the number of years since the car was purchased. Determine whether the model represents exponential growth or exponential decay. Identify the annual purchase increase or decrease in the value of the car. Estimate when the value of the car will be $8,000. A part says determine whether the model represents exponential growth or decay. So if we look at the model again, we see that B, remember this is A and this is B. B is greater than 0 but less than 1, so this represents exponential decay. So this one is exponential decay. Identify the annual purchase increase or decrease in the value of the car. All right, so exponential decay can be found by doing 1 minus the rate. So 1 minus the rate would be 1 minus 0.15 or 15%. 1 minus 15% leaves us 85% here. So for B part, we're going to do 1 minus 0.15. That equals the 0.85. So that represents it decays at 15% annually. And it says number of years since the car was purchased. So that's why I'm saying annually. All right, and C part, estimate when the value of the car will be $8,000. So we're going to use the model and we're going to estimate when the value of the car is $8,000. Remember, the value of the car Y is in thousands of dollars. All right, so instead of substituting 8,000, we can just substitute 8 in place of that, knowing that it's in thousands of dollars. So 8 equals 25 times 0.85 to the t power. And we can use technology, or we can use our calculators to graph this and see when y is about 8 or $8,000. So we can type in 25 times 0.85 raised to the t power. You may have to change your window a little bit. A 10 by 10 may do it, but looks like my window is zoomed out a little bit, so you may need to do the same. All right, so what are we looking for? We're looking for when the y value is about 8. So when the y value is 8, x is 7. So there is a point, 7, 8. So what does that mean? So t is time in number of years. So it says after 7 years, and this would be about 7 years. After about 7 years, the price of this car is about $8,000. So A part is exponential decay. B part says identify the annual percent increase or decrease. We said it was a decrease by 15%. And then C part, estimate when the value of the car will be $8,000. So the value of the car will be $8,000 after about 7 years. Example 3, writing an exponential model. In 2015, the world population was about 7.38 billion. During the next 5 years, the world population increased by about 1.09% each year. Write an exponential model that represents the population Y in billions t years after 2015. Then estimate the world population in 2020. All right, so the first thing we're going to do is write down our exponential equation. So we know this is going to be exponential growth, so it's going to be A times 1 plus your interest rate to the t power. Then we can just plug in what we know. Our initial amount, A, is 7.38 billion. And then we're going to have 1 plus the interest rate. So when we write this in our equation, we have to change this to a decimal. So remember, you change it to a decimal by moving it 2 decimal places. So I'm going to move it past the 1 and then add a 0. So 0, 1, 0, 9, and then to the t power. So we're going to have 7.38 times 1.0109. And then we want to estimate the world population in 2020. 2020 is 5 years after 2015. So it says in 2015, the world population was this. During the next 5 years, the population increased. Write an exponential model that represents the population t years after 2015. So t years after 2015 means we only go from 2015 to 2020, which means we're looking at 5 years. So what we're going to do is estimate this when t is 5. So 7.38 All right, make sure you've got it all typed in correctly. And it's going to be about 7.79. And remember, that's in billions. So in the year 2020, which now we know that's already in the past, but the world population would be about 7.79 billion.